Hey everyone, it's Justin again. Today we're going to be exploring a special type of function called reciprocal functions. By the end of this lesson, you should be able to recognize the graphs and properties of reciprocal functions. First, we'll define reciprocal functions. Then we'll sketch their graphs. We'll discuss some properties of these functions, and then we'll work through a couple of examples. As a reminder, the reciprocal is what you get when you flip a fraction. The reciprocal of 2/3 would be 3/2, and the reciprocal of 7 would be 1/7, since you can think of 7 as being the fraction 7/1. This applies to functions as well. The reciprocal function of x would be 1/x, just like how 7 became 1/7. And the reciprocal function of x squared would be 1/x squared. So if f of x is a function, the reciprocal function is the reciprocal 1/f of x. Now, what does f of x equals 1/x look like on a graph? One way to get a sense of what any graph looks like is to plot some points. We'll create a table of values to keep track of our information and to help us find some patterns. Most people would probably start a table of values at x equals 0, but for this function, we can't do that. 1/0 is undefined, so we'll just start at 1 instead. If x equals 1, then f of x is 1/1, which is just 1. So let's plot the point 1, 1 on this graph. Now let's plug in 2. F of 2 is 1/2, so we can plot the point 2, 1/2. F of 3 is 1/3, and you may be starting to notice a pattern that can help us fill in f of 4, and really as many points as we want. For any integer we plug into this function, the output will be 1/, that integer. Note that the y values keep getting smaller and smaller as we increase x, but no matter how high a number you start with, 1/, that number is always going to be positive. It would get closer and closer to 0, but it could never reach 0 exactly. Does that sound familiar? That's the definition of an asymptote. So this graph will have an asymptote at the horizontal line y equals 0. This gives us a good idea of the shape from the x value of 1 onward, but we know that we can't plot a point at x equals 0. So what do you think will happen between 0 and 1? Let's graph some points in that area to see what it looks like. A good number between 0 and 1 to start with is 1/2. So what would f of 1/2 equal? F of 1/2 would be 1/1/2, and 1 divided by a half is 2. So we can plot the point 1/2, 2. If you think of some other fractions between 0 and 1 that will give us points that aren't too difficult to plot, think about what happened with 1/2 to make it come out as a nice and simple 2. And let's see if we can get that to happen again. What points could we plot next? Here are some other points that come out to whole number values for y. Let's plot 1/3, 3, 1/4, 4, and 1/5, 5. Now, what seems to be happening on this part of the graph? If you're thinking it's another asymptote, you're correct. We can go as close as we want to 0. We can plug in 1/1,000,000,000, but we can never plug in exactly 0 into this function. So there is an asymptote at the vertical line x equals 0. Now let's just connect the dots. We get this shape, like a steep slide. And of course, it goes infinitely high on the left side and infinitely long on the right side. This is the general shape of 1/x. But that's only half of it. We haven't looked at the left side of the graph yet. This function doesn't exist at 0, but it does exist at all negative numbers. Luckily, it's essentially the same. If we start with negative numbers, we get similar outputs, they're just negative now. The left half looks the same as the right half, but upside down and facing the other direction. Now, our sketch of 1 over x is complete. Notice how the vertical and horizontal asymptotes separate this graph into multiple pieces. This is typical of many functions like 1 over x. The shape of the graph will look pretty familiar by the end of this unit. Another basic reciprocal function is 1 over x squared. What do you think it'll look like on this graph? Let's keep the green points for 1 over x on the graph to compare the two functions when we're done. So we'll use blue squares for the points of 1 over x squared. On the right side, it looks pretty similar. At x equals 1, 1 over 1 squared is still 1. So the point 1 comma 1 is on this graph too. At x equals 2, instead of 1/2, we have 1/4. So we plot the point 2 comma 1/4. And at x equals 3, instead of 1/3, we have 1/9. We plot the point 3 comma 1/9. At 1/2, we'll have 4. So we plot 1/2 comma 4. And at 1/3, we'll have 9, which is already off the graph. Let's connect on this side. So the shape is very similar. Do you think it'll look this similar on the left half of the graph where the x values are negative? Think about each of these x values, but negative. The x values get squared in this equation, which will make all the outputs positive. For example, 1 over negative 1 squared will still be positive 1, so it will still be above the x-axis. So these are the points we're plotting, apart from negative 1/3 comma 9, which again is off the graph. Connect the points on this side, and now we have our sketch of 1 over x squared. The graph of 1 over x had one side pointing down, but this graph of 1 over x squared has both sides pointing up. But both still have a similar structure, a horizontal and vertical asymptote at 0, and multiple parts of the graph separated by these asymptotes. Now, since we've reviewed domain and range in the last couple of lessons, let's talk about the domain and range of these functions. For the domain, what numbers can be plugged into 1 over x and 1 over x squared? Well, it's sometimes easier to ask the opposite question. What numbers cannot be plugged into 1 over x and 1 over x squared? Well, what is the only number that can't be the denominator of a fraction? It's 0. Seems like it's always 0 making things difficult, isn't it? The domain of both of these functions is all real numbers except 0. Do you remember how to write this in interval notation? We're going to need 2 intervals, one on either side of the 0 with soft parentheses because 0 is not included. For the range, it will be different between these two functions. So let's look at 1 over x first. The function stretches both infinitely high and infinitely low. But there is that horizontal asymptote. The function can never be 0 exactly. That's because the equation 1 over x equals 0 has no solutions. Try multiplying both sides by the denominator of x. There is no value of x that can make 1 equal 0. So there's no value of x that can make 1 over x equal 0. That means 0 is also the only number not included in the range. So both the domain and range are all real numbers except for 0. Don't feel bad for 0 though. If 0 wants to get included in more functions, it should start by not causing as many problems. Now for 1 over x squared. Again, the domain is all real numbers except 0, since 0 is the only number we cannot plug into this function. As for the range, there is still an asymptote at 0. But this time, The function never goes below that asymptote. So what's the range? And can you write it in interval notation? The range is all real numbers greater than 0, which is written as the interval 0 to infinity. Again, since we are not including 0, we will use soft parentheses. All right, now that we've explored these reciprocal functions, it's time to move on to some examples to apply our knowledge. If f of x equals 1 over x and g of x equals 1 over x squared, what are the values of f of 1/4 and g of 1/4? These are reciprocal functions, but they are still regular functions. We can plug the values in as we would for any other function. So let's start with f of 1/4. If we plug in 1/4, that gives us 1 over 1/4. This is the same as 1 divided by 1/4. Changing this division into multiplying by the reciprocal gives us 1 times 4 over 1. So f of 1/4 is 4. Next, let's calculate g of 1/4. This is 1 over 1/4 squared. 1/4 squared would be 1 over 16, so this is the same as 1 divided by 1 over 16. Keep change flip again, and we have 1 times 16 over 1. So g of 1/4 is 16. And now we have our answers. Next, let's do one more example. Which of the following values are not included in the range of g of x equals 1 over x squared? Choose all that apply. And our options are 0, 1, -1, and the square root of 2. Recall our graph of 1 over x squared, and recall that the range is from 0 to infinity. We can check to see if each option falls within the range interval. Try it now with these 4 numbers. Which of them fall in the interval 0 to infinity exclusive, and which of them do not fall into this interval? Well, 0 does not fall into this range interval because the soft parentheses tell us to exclude it. Recall that 0 is the horizontal asymptote of this function. The function can never equal 0, so 0 is not in the range. 1 is within the range. It's greater than 0 and clearly less than infinity. It falls within the interval, and that means that it is a possible output of this function. -1 is not in this interval. Therefore, it's not in the range. In our graph, you can see that -1 falls under the asymptote, and the graph doesn't exist in that bottom half. So -1 is not in the range. And lastly, the square root of 2 is within the range because it's a positive number. So it falls between 0 and infinity. Remembering that the question has asked us which values are not included in the range, the answers are that the numbers that did not fall within this interval are 0 and -1. In this lesson, we learned about the reciprocal functions 1 over x and 1 over x squared. Next time, we'll explore how the properties of this function change when we move it around the graph. See you then! Hey.